So I just want to go back. While we're talking about vectors and look at number, what is that, 4. Flip back onto the front on number 4. Number 4 is about a tennis ball. And the tennis ball, 60-gram tennis ball, is moving at 25 meters per second and strikes a wall at an angle 45 degrees. So the wall is here. The tennis ball is up here somewhere. And it's coming down like this on an angle of 45 degrees to the wall. It then rebounds off of the wall with the same speed in a new direction. This vector is pointed at 45 degrees less than 360. This vector is pointed at 45 degrees less than 270. This one points down and to the right. This one points down and to the left. So they are not the same. Right? That's very important. So if this particular setup, it makes it pretty easy because they're all 45 degrees and everything is the same. We know the hypotenuse is 25 meters per second. Right? And so what we have to imagine is that momentum is conserved. And so the question is, what is the impulse? The impulse is the change in momentum, right? Delta P. But delta P is built out of a change in momentum in the x direction, vector addition-wise, to a change in momentum in the y direction. And so before we can analyze how this changes, it's important to analyze the x and y independently. That's exactly right, Connor. Very good. So just like we saw before, what I'm going to do is I'm going to draw each one of them as perpendicular components, right? So I'm going to say that this one is pointed to the right and down. And I'm going to say this one is pointed down and to the left. Before I move on, I'm going to remind myself that P is actually what's conserved, right? And what's mainly represented by this vector as opposed to the velocity. So before I can do anything, I need to do m times v before I start finding the sides of the triangle. Because it's not the 25 that is conserved, right? It's not the speed, it's the momentum. So I have to take the mass, which is 0.06 times 25 to get an original momentum of 1.5 kilogram meters per second. The original momentum is 1.5 kilogram meters per second. The final momentum has a magnitude of 1.5 kilogram meters per second. But as a vector, they are different. And since the direction changes, the momentum changes. Whereas, since this is traveling at 25 meters per second and this is traveling at 25 meters per second, the energy does not change, right? Because if it's 25 meters per second times 1/2 mv squared, the total energy is the same both before and after. And that should make sense. A ball hits a wall, it turns into potential energy, bounces back off, turns into kinetic energy. The total energy is conserved because energy is not a vector. But because momentum is a vector and the thing has changed direction, then it has experienced an impulse, a change in momentum. But when we go through and resolve these components, right, 1.5 being the hypotenuse, not 25, right, I find the sides to be 1.1, 1.1, 1.1, 1.1, right? Except that when we apply our proper frame of direction, this is positive 1.1 and is px. This is negative 1.1 and is py. This is negative 1.1 and is py prime. This is negative 1.1 and is px prime. Again, because p was 1.5 and p prime was also 1.5 in a new direction. So, of course, I can take the easier of the two cases first. The change in momentum in the y direction, right, would be the final momentum in the y direction minus the initial momentum in the y direction, which is negative 1.1 minus negative 1.1. And since the ball is going down with the same angle magnitude in the same direction, the momentum in the y direction does not change. So delta Py is 0. Whereas in the x direction, delta Px is Px prime minus Px, which in this case is negative 1.1 minus positive 1.1, which means that delta Px is not 0, but is instead negative 2.2. Yes. So in a closed system, change in P should be 0. But this is not a closed system because it hit a wall. And so the interaction with the wall causes the ball to change momentum.
So more momentum or less?
Less. It's lost.
Negative 2.2 momentum.
Yeah, exactly. That's the change. It now has a negative 1.1, and it had a positive 1.1, so the change is negative 2. Exactly. So the change in momentum is Px plus Py, change in Px and change in Py, added as vectors, right? In this particular case, there are no vectors to add together because Py, change in Py, is 0. If this had a magnitude because this came off at an angle that was not comparable, it was not 45 degrees, but was something different, then these two sides would be different lengths, and these would actually be two different vectors, which means the change in momentum would be a triangulation of the sum of those two vectors. And you can see how it kind of all puts it together. Does that make sense? So in this case, it's just a matter that this is equal to the change in momentum in the x direction, which happens to be negative 2.2 kilogram meters per second, which is the final answer for this particular problem. But you can imagine that if this bounced and had, I don't know, do you call it English in tennis? In pool, you call it English, right? When you hit the ball and it's spinning and it hits the wall and spins off at a weird angle, right? Yeah. And I don't know what you call it. Yeah, do you call it English in basketball too? Yeah, no, what do you call it? What do you call it in tennis? Like if you hit a slice so that it's spinning, backspin. Sure. So you can imagine that if this had spin, it's possible that the ball hits the wall and then goes in some new direction, right? At some new speed. And so that would change what Py prime is and what Px prime is. And so then I end up with two values that are not in the same parallel direction, right? And so then the changes are actually a vector that I'd have to draw the triangle for. That makes sense?